This video is on graphing rational functions, part 1. We need to begin by deciding what a rational function actually is. While you don't need to copy all of this, you should make some notes and maybe jot down a couple of the examples and why they are or aren't. In the first expression that you see here, we have a rational function, and the explanation is that it's the ratio of two polynomials. So it's important to understand that a ratio is just a fraction comparing two things, in this case polynomials. The second one is also the ratio of two polynomials. It is a simpler form of polynomials. Remember that a plain number technically meets the requirements of being a polynomial. If you recall from previous lessons, a polynomial must have whole positive exponents, so no fractions and no negatives. And this does meet those requirements. It must also have real coefficients. There are no imaginary numbers involved here, so it does meet the requirement of a polynomial, even though we have quite simple polynomials. This third one technically is also a rational function. And these are all expressions, but if you put a y equals in front of them, that's what makes it a function, an input and an output, an x and a y. So generally, we'll think of a rational function as having a variable in the denominator. And in this case, there is no variable, no x in the denominator. It does technically meet the requirements of being a rational expression or function, but we won't actually think of it that way. If you look at this next one, the numerator isn't a polynomial. And of course it says it here, it's because of the radical, but think about why. What have you learned about how radicals could be written as exponents that make this not a polynomial? The square root can be written as a power of 1/2, and if you recall, the definition of a polynomial does not allow fractions as exponents. And so since the numerator is not a polynomial, this expression is not a rational expression. You won't see much in the way of the last one, but I did want to include it here so that you know it can happen. It looks like it would be a rational expression. It isn't in the form that it is here, but if we simplified using some algebra, this would be the math, and it would turn into a rational expression. The following graphs on this slide are examples of the way rational expressions can look. Now, in class, you did a discovery activity to see what the parent rational function looked like, which is y equals 1/x, and you did some graphing with your Desmos graphing calculator to help you decide what different pieces of a rational equation do to the graph of that function. Well, we didn't really look at all the different types, but you should know that rational functions can look quite different when we graph them. And so these are just some examples that you should put in your notes. The main thing that I want you to notice here is that there are what's called asymptotes. And in these graphs, the asymptotes are denoted by dashed lines. An asymptote is really an invisible line that a graph approaches but never touches. Now I say invisible because it's not part of the graph, so we actually draw them in with a dashed line so that we can use them as guides, because those asymptotes will sort of hug the pieces of the rational graph. And you can see that, let's say in graph D, these blue curves approach but never touch, those vertical asymptotes, and same thing here. It approaches but never actually touches this horizontal asymptote. Keep in mind that even though it looks like it touches it, it can't by definition of what an asymptote is. If you think about the parent rational function, And you know that from your investigation, it looks like this. And the x and the y axis are the asymptotes, which means that my green curves approach but never touch those axes. If we think about what's happening, let's say x gets bigger. Well, when x is 1, y is 1. When x is 100, y is 1 over 100. When x is 1,000, y is 1 over 1,000. So as we're plotting those points, if you think about where they're located, they're always above the x-axis. Now just slightly, and that space gets smaller and smaller. Can this value of 1 over x ever be 0? The only way a fraction could be equal to 0 is if the numerator is 0. And that's not possible. We have a constant in the numerator here. So this will never be equal to 0. Not only that, but as x increases, the value of y will never be negative. So it will never go below the axis either, unless x is actually negative, which sends us to the left on the graph. And so this is the concept of an asymptote, where no matter what value of x we put in, we are going to get close to some number. So as x approaches infinity, y actually approaches 0. This is the general form of the equation of a rational function. And in our warm-up in class, you saw that we changed the values of a, h, and k using Desmos to help us discover what each of those values do to the way the graph looks. So here's sort of a cleaned picture of what the parent rational function looks like. And it's important that you know the most basic rational function is y equals 1 over x. And if we made a table of values and plotted points, we would get these green curves. The red dashed lines are the asymptotes. In this case, for the parent function, the asymptotes happen to be on the x and y axis. It's also important to note a couple of points on the parent function because it will help us to decide whether our new function or some transformed function has particularly a stretch or a shrink. And so the fact that the point 1, 1 is part of the parent function helps me to know that if I can go from where the asymptotes intersect over 1 and up 1, and that point is on the graph, then there has not been a stretch or a shrink when we look at a new graph. Let's take a look at an example so you know what I mean. From the warm-up in class, we determined that the value for a is what tells us whether there's a shrink or a stretch. A whole number will be a stretch, and while it would look funny, if there was a fraction in the numerator, that would be a shrink. Also, it's important to note that a negative value here is a reflection over the horizontal asymptote. And I'll put capital H, capital A for horizontal asymptote, which means it just flips it upside down if A is negative. The value for H, that's the one in the denominator with the X. This moves the graph left or right. And just like it has worked for all the functions you've studied since 9th grade, you will find that that one does the opposite of what the sign is in the problem. So if we have a plus 3 with the x, it's going to move left 3 instead of right 3. It sort of does the opposite of what you intuitively think it would do based on the sign. K is tagged on to the end, and that's what moves the graph up or down. So let's look at an example here. And in this case, our graph of our rational function is in red, and our asymptotes are in green. The first thing that I want you to do is write the equation of those asymptotes. The asymptotes of rational functions will be horizontal and vertical lines for the most part. We will look at rational functions with slant asymptotes a little later. To write the equation of a vertical line, I want you to look at which axis that line touches. It touches the x-axis, and so the equation of that line is going to be x equals. So now answer the question, where does that graph touch the x-axis? And it touches it at -3. So the equation of this vertical asymptote is x equals -3. You do the same thing for the horizontal asymptote. Ask yourself which axis it touches. It touches the y, so this is y equals. Where does it touch it? At +1. And so the equation of this horizontal asymptote is y equals 1. A lot of students struggle with writing the equations for horizontal and vertical lines, and this is an easy way for you to do that. We're going to describe the transformation first. So you know that from the parent function, the asymptotes cross at the origin. This is the point you'll want to compare to the new place where our new asymptotes cross, and that will describe our transformation. From the original, we move up 1 and left 3 to get to the new place that our asymptotes cross each other. And so we have sort of a reference point that we can use. This tells me that the graph moved up 1 and left 3. I can use that information to write my new equation. I know that there is no stretch or shrink because from this point where the asymptotes cross, if I move over 1 and up 1, this point is on the graph, which means A is just 1. Since I moved left 3, I do the opposite and I put x plus 3, and up 1 tells me there's a +1 at the end. This is the graph of this red function shown. You try one now. I've noted these in case you can't read them on the screen. I want you to write the equations of the asymptotes, describe the transformation using words, and then write the equation. Pause the video and try it now. How'd you do? Make sure that you jot down any questions that you have to ask in class. The last concept we're going to cover is what happens when there's a stretch or a shrink. And if you'll notice, when you look at these asymptotes, if I move over 1 and up 1, the point that would be on the graph if there was no stretch or shrink would be right here. But this point is not on the graph, and so there must have been a stretch or a shrink. And the way we handle it is going to be to do everything we can do to write the equation, but we'll leave A in the numerator, and I'll tell you what we're going to do with that in a minute to find that value. So since this from the parent function moved right 1 and up 3, I know that this is x minus 1 for right 1, and up 3 is +3. Now, if I knew a value for x and y, I could use it because then a would be the only unknown variable, and I could figure out what the value of a was. But I do know an x and a y. They give me a 0.25. So what you're going to do is plug those in for the x and the y. Keep a because that will be what we're solving for. When you solve this equation, we get 5 equals, a over 1 is just a, and a is equal to 2. That means I can rewrite my equation with a 2 where the a goes. And that's how I know what my stretch or my shrink is. You should try the next one on your own. I've noted the asymptotes and where they're located so that you can write the equation, and we'll check it together in class. Part 2 will give you the rest of this lesson.